Hello everyone, welcome back to the course on Chemical Reaction Engineering 1. Myself Nidhi Mehta, Assistant Professor at Chemical Engineering Department, LSA Institute of Engineering and Technology. So let's just start our course with today's topic, which is again under the cover of Overview of Chemical Reaction Engineering. We have started this chapter in our previous sessions and we have already covered important terminologies related to CRE such as kinetics, chemical process, chemical thermodynamics, and what is rate of reaction, what are various parameters which can affect rate of reaction, and also we have covered what are different ways or method to represent rate of given reaction, right. So depending on the basis we are selecting, we can have different ways of writing the rate of reaction. After that, we have also seen ideal reactors. So in case of ideal reactors, we know that ideal reactors, when we are talking about, there are three different reactors. First one is batch reactor. In case of batch reactor, feed or the reactant are feeded into the reactor at once, and after providing the enough residence time, we withdraw the entire product. In case of CSTR or PFR, both of them are continuous reactor. That's why we are getting product continuously once we start the process, right. So now let's just start today's session, which is based on concentration dependent term of rate equation, right. So first term is single and multiple reaction. The second one is elementary and non-elementary reaction. Then there is molecularity of reaction, and last one will be order of reaction. So these are the terms which are dependent on concentration and it affects the rate of reaction or rate equation. One by one we will study this in brief. So let's just start with the first one, which is single and multiple reaction. So what do we mean by single reaction, right? Single reaction, when we are talking about, are those reactions when a single stoichiometric equation and single rate equation can be chosen to represent the progression of reaction. That is, how your reaction is proceeding or how it is taking place can be represented using single stoichiometric reaction, then it is termed as single reaction. For an example, this, right, when we are saying AB is one reactant, C is another reactant, when we combine both of them, that is when AB reacts with C, we get BC as a final product and A is a side product, right. So this is a single reaction where the way of writing and the way reaction is actually being proceeding is same, right. The reaction is happening in the same way it is represented. So this is single reaction. The next one is multiple reaction. So what do we mean by multiple reaction? When more than one stoichiometric equation are needed to represent the kinetics of entire reaction, then it is known as multiple reaction. For an example, this reaction, right. We are starting with reactant A and we need S as a final product, right. We have only fed A into our reactor and we are withdrawing S as our product. But in between A and S, that is when in the process of formation of S, there is one time period when R is formed, and R is nothing but intermediate product, right, or intermediate reactant. So what is happening is A or reactant A is initially converted into some intermediate product which is R, and that R is again reacting and then it is giving you the final product which is S. So for this case it is a multiple reaction because we are feeding A and we are withdrawing S, but in between A and S there is one more step, that is formation of R and formation of S from the R, right? Then there is a parallel reaction, right? So what do we mean by parallel reaction? When single reactant is consumed in two different paths, then at that time it will give you two different products, or there may be two reactants giving you two different products, right? So this is like A gives you R and A gives you S. So this is again a multiple reaction, and A gives you R and B gives you S. So this is again a multiple reaction. Or there may be a complicated reaction like this, where A plus B combines together to form some intermediate product R, and that intermediate product R again combine with one of the reactant to give you your desired product. So as you can see here in this reaction, that A combines with B. A and B are reactants. So both the reactant combines to form intermediate product, which is R. And that intermediate product R is again combining with one of the reactant, which is B, to give you your desired product S. So this is known as complicated reactions. Now coming to the next topic, which is elementary and non-elementary reaction, which is again the concentration dependent term for rate equation. So what do we mean by elementary reaction? Consider that we are having a single reaction whose stoichiometry is A plus B giving you C, right? So for this, rate of reaction, that is rate of disappearance of A, can be written as minus Ra equals to K Ca into Cp, right? Why we are putting the minus sign here? Because A is the reactant and it is going to get consumed, and then only product can be formed. So minus Ra is representing rate of disappearance of A, K is the rate constant, Ca concentration of A, Cb concentration of B. So this is elementary reaction. Elementary reaction are basically those reactions whose rate equation can be easily written, right, in the simplest form like this. But when we are talking about non-elementary reaction, right, so we cannot represent the stoichiometry directly in its rate equation. So hydrogen and bromine, when they react to form hydrogen bromide, so it is the given reaction, but the complicated rate equation can be obtained. Since it is a non-elementary reaction, that means the reaction of the reaction, that is H2 plus Br2, is taking place in multiple steps, and due to that its rate equation cannot simply be written in this particular form. So it will have the complicated form of rate equation. So that this is known as non-elementary reaction. Then there is a molecularity of reaction. So the molecularity of reaction is basically determining the number of moles which are reacting, right? Suppose we are talking about unimolecular reactions, then there is single mole which is going to convert into desired product. When we are talking about bimolecular reaction, as you can see here in the example, A plus B is giving me the product. So its rate equation can be written as minus Ra equals to minus K Ca into Cb, right? And there is a trimolecular reaction where three reactants combining together to give you desired product. And the last one is order of reaction. So basically what do we mean by order of reaction? The order of reaction is basically refers to power dependence of the rate on concentration of each reactant, right? For an example, as you can see here, I have put different examples here. 2N2O5 in gaseous phase reacts to give you 4NO2 plus O2. So if you see the power of this reactant here, then it is 1, right? So power of reactant is 1, so order will be 1. If you come to this particular reaction, 5 bromine minus plus BrO3 minus plus 6H plus gives you this kind of product. But here if you see that this is minus and this is plus. So if you combine their powers, then it will be 1 plus 1 plus 2, which is giving you 4. Right. So, how it is coming to be 1 plus 1 plus 4? Here you can see easily using your rate equation. Right. So, this is how we calculate order of reaction. So, this is all about today's session. Hope all the things which we have covered today is quite clear. Before completing today's session, I will give you a quick recap of what we have covered today. So, in today's session, we have covered what are various forms of rate equation, right? That is, what are various forms in which we can represent the concentration dependent term of rate equation. For that, we have started with the first, single reaction and multiple reaction. In case of single reaction, the equation and its rate representation is similar, that is the stoichiometry of equation and the way of representing the rate equation is similar, whereas in case of multiple reaction it is varying, right. Then there will be a elementary and non-elementary reaction. After that we are having the term molecularity of reaction, where number of moles which are taking place is taken into consideration, and lastly we are having order of reaction. So, I just hope whatever topic we have covered today is quite clear. Thank you.